Hello, everyone. Isaiah here. We'll wait for the program to kick in, and then I'm going to ask you if you can hear me okay. So it looks like we have some of you on a little bit early. If you can hear me, please type in yes into the chat box. We have a slight delay here, so it might just take a minute for you to be able to hear me and see my slides. But if you can hear me and see my slides, please type in yes into the chat box real quick, if you would. We'll just make sure that the audio is indeed working. There we go. Thank you, Ben. Thank you, Michelle. Thank you, Marie. Thank you, Chelsea, Vanda, Ben. Appreciate that. Andreas, Raiden, welcome, welcome, welcome. Slight delay there, but it looks like we have quite a few of you on already. Very excited to have you here. I am Isaiah, and we are going to be doing a short introduction on today's presentation, which will be done by Tim Bushnell. So you are in the right place if you came to see Tim's advanced compensation webinar. So specifically, the webinar title is Improve Experimental Reproducibility with these advanced 4 to 18 color compensation strategies. You will learn 4 to 18 color compensation best practices. You'll learn how to stop wasting time, money, and other resources on faulty experimental design. Tim will talk about some compensation myths and how to overcome them. He'll talk about the compensation rules that you need to know, the rules that publication, grant, and patent reviewers require you to follow. One thing Tim really likes to see is where everybody is from. So if you can do me a favor and type in, your name should show up if you put it in already. It'll show up in the chat box. But please type in the city or country that you're in currently. What is the city and or country you are in currently? Tim loves to see this. I know we have people joining from all over the world. So we have Eamon from Italy, welcome. Sean from New Jersey, welcome. Alicia from Syracuse, welcome. Vanda from Croatia. Raiden from Vancouver, Stephanie from Rockville, Akos from Cambridge, Tadek from Durham. Welcome, Tadek. Helena from Copenhagen. Good to see you. Sean from UK. Anna from Lisbon. Terry from Memphis. Jana from Ottawa. Mariana from Toronto. Katie from Glasgow. Yago from Stockholm. Mauro from Philadelphia. Jeffrey from Philadelphia. Are you guys together right there? Watching this at the same time? It's cool that you both came up, both from Philadelphia, back to back. Elizabeth from London, Maria from Brazil, Mohammed from Ann Arbor, welcome. Eris from Boston, Christos from Barcelona. I'm going to try to say as many names as I can, clearly. James from Richmond, Paula from Cleveland, Alisa from Sweden, Hannah from London, Marie from Singapore, wow. Elliot from Kent, Ohio, Anna from Baltimore, Elke from Utrecht, the Netherlands, welcome. Daniel from Minneapolis, Yaking from Jacksonville, Florida, Otavio from Brazil, Anna from Germany, Burnett from South Africa, Jasneet from India, Delhi, India. Wow. Karen from Denmark. Luis is also from the Netherlands. Jacobo is in Mexico right now, welcome. Melissa from Argentina, Catalina from Spain, just people from everywhere. Carlos is in Rochester. Are you right next to Tim? Because I know Tim's there too. Maria from Maryland. Mohammed also from Singapore. And wow, just people from everywhere. So thank you all for joining. Thank you for sharing that. Really appreciate it. Because you've taken the time to be here with us today, we do have a free gift for you. It's a free video training, the 5 best practices of advanced flow cytometry. And you can get this for free. All you have to do is go to a link, which I'm going to put in the chat box here. If you go to this link, you're going to be taken to the page that you're seeing on the screen here. Okay, I'm going to put this at the very top of the chat box. It should show up for you in green at the top of the chat box. If you click on that link, you're going to be taken to the page you're seeing right now on this slide. And all you got to do is click that blue button there that says Send to Messenger. And this will take you to your own Facebook Messenger. And then all you do is type in the word flow. Just the word flow, F-L-O-W. Don't get too excited and type in flow exclamation point, because then it won't trigger the gift to be sent to you. But if you type in the word flow, you're going to automatically get this training video, 5 best practices of advanced flow cytometry. So again, click that link at the top of the chat box. It's manychat.com/L1/expert cytometry. You'll be taken to this page you're seeing here. This is your only chance to get this. We will remove the link after Tim gets on. So you want to click that link and then click the blue button, send to Messenger. And then essentially you just want to message Tim the word flow. On Facebook Messenger, you can go to the Expert Cytometry fan page and do it there too, but just click that blue button, type in the word flow, and you will get this gift for free just for showing up. Also, Tim will talk to you about a mid-webinar bonus. So about halfway through the webinar, he's going to mention this bonus that you can get for those of you who are interested in learning more about flow cytometry and becoming experts, not just in compensation, but beyond. You'll get a chance to get this free bonus. It's 2 videos on compensation and controls, advanced training videos that you can watch. This is a course that normally costs $200 to have. These are advanced videos that Tim has done. It's a 2-video mini course, and you will get a chance to get them for free, again, about halfway through the webinar. So again, we're going to start here very soon. You are in the right place. If you want to see Tim's advanced compensation webinar, specifically, he is going to talk about 4 to 18 color compensation best practices. He is going to debunk compensation myths, maybe some that you're following right now that are giving you erroneous data that are going to prevent you from being published or getting a grant or getting a patent. And so what he's going to do is he's going to talk about the new rules of compensation that publication, grant, and patent reviewers want you to follow. Okay, so this is the man of the hour. This is Tim Bushnell. I think he's looking into the sun here. Can't quite tell. But Tim did his postdoc at the University of Rochester, which is shown here on this slide. This is the University of Rochester. And now, of course, he's the director of the University of Rochester Medical Center's flow cytometry facility, or he was from 2003 to present. Actually, he's the director of the facility, but he's gone on to be the director of all of their research cores. And I'll talk about that in a second. But he became the director of the University of Rochester flow cytometry facility again in 2003. So that was, how many years ago is that now? Geez, like 15 years. He's also an executive committee member of ISIC. This is a flow cytometer for those of you who don't know. He's also a executive committee member of ISIC, the International Society for the Advancement of Flow Cytometry. He's been an executive committee member for 2008 and has served on their board as secretary and as co-chair of the Membership Services Committee. So, of course, this is the committee in terms of flow cytometry, and Tim is on the board. He is an expert in the field, and you can't learn from anybody better or anybody who knows more about flow cytometry. So this is an example of a shared resource facility. I just like to show this because he's gone above and beyond just being a flow cytometry facility director. He's now the director of all of the University of Rochester Medical Center's research cores, all of them. And he was given this role in 2012, and he's been in that role, of course, for about 6 years now. After becoming director there, Tim started Expert Cytometry. So if you've never heard about Expert Cytometry, you can go to expertcytometry.com to learn more about it, expertcytometry.com. There's a bunch of free materials there, some free ebooks that you can get your hands on, articles that Tim writes and publishes, a couple of them every month that you can look at as well. So he founded Expert Cytometry in 2012. And again, this was 6 years ago, so he's been running Expert Cytometry for 6 years too. His specialties are flow cytometry, design of polychromatic panels, of course, compensation, data analysis, quality control, and much more. He's also worked with many of the world's largest companies and institutions, consulting with them, helping them, giving them direction in terms of flow cytometry. You can see some of them here, including Bio-Rad Laboratories, BD Biosciences, Beckman Coulter, MedImmune, Thermo Fisher, Regeneron, and many, many more. But Tim, he started Expert Cytometry with the goal of taking training to as many people as possible, to as many scientists as possible. And there was a time where I think he was doing, just dozens and dozens and dozens of live trainings every year. But he saw the need for training for flow cytometry outpaced his ability to be everywhere at once. So what he did was he started the Flow Cytometry Mastery Class, a place, essentially a virtual home base for people who wanted to learn about flow cytometry and wanted to learn best practices so that they could get their data published. So you should be seeing a slide right now of the mastery class. I want to make sure we're caught up here. There was a slight delay. So if you're seeing a slide of the mastery class, please type in yes into the chat box for me. We're just about done with our introduction, and I'm going to bring Tim on. We do this introduction because it allows everybody to trickle in As an example, we've had over 100 people join since I started the introduction, and also so that Tim can focus exclusively on compensation. So there's no questions about, hey, what is expert cytometry, or hey, who is Tim? Okay, so it looks like we're all caught up there. Thank you, Deb. Thank you, B. Thank you, Maria. The masterclass, in terms of what it is, again, it's this home-based, this training program specifically for everything you could ever want to know about flow cytometry. It keeps you up to date with best practices, whether you are a new user or a power user who's an expert in the field. There are webinars that occur every couple of weeks, brand new webinars interviewing top people in the field on top specialties, people who work with different cell types or who are using different technologies, different methods. There's more than 40 advanced training videos. There's core content with Tim teaching in front of a whiteboard, Tim giving sessions in front of an instrument. There's workbooks, and of course, a private group where you can get your flow cytometry questions answered almost immediately. Tim, of course, is more than just a flow cytometry nerd, and I say that with love. He's also a dedicated dad. He volunteers with his son's Boy Scout troop. This is his son Nathan here, Troop 111. So without further ado, I'm going to bring Tim on here. Put away your cell phones, your distractions. Tim will save time towards the end. He's really good about this. He answers a lot of different questions. So please be respectful in the chat box. Listen to the material Tim has. And if you have questions, you can save those for the end. So I'm going to bring Tim on here. I'm also going to take away this ManyChat link at the very top. So you want to click on that link now and message Tim the word flow on Facebook Messenger if you want that bonus. All right, so I'll bring Tim on now. I'll give him the wave for the handoff here. We should be able to see him here in just a second.
Hey there, Isaiah. How you doing?
Maybe. There we go.
There we go. Yep.
All right, Tim. Thank you very much.
Yeah, thanks. Talk soon. Okay. Hello, everyone. Welcome. Let me just share my slides. For those of you who have gotten up early or stayed up late, thanks for showing up. I do want to make a shout out is if Marwan Ishmael, I hope I said your name right, is on. I saw you posting on Facebook promoting the course. Thanks a lot. Appreciate that. So today we're going to talk about compensation, and we're going to the goal today is at the end of this webinar you're going to understand the principles of compensation, have a better idea of the best practices, and I'm going to try to help debunk some of the myths of compensation. We're going to talk about 4 to 18 color compensation best practices. Everything we're going to talk about applies at every level, no matter how many colors you're doing. If you have more colors, it just takes more time, and there may be more consequences we have to deal with. We're going to talk about, some of the compensation myths that are out there. Compensation has been around for a number of years, and people still get frustrated or concerned with it even today. And kind of the rules that will get you good compensation, that when I and others are reviewing papers, we look to make sure that things like that have been followed. So let's start off. Sorry. Here is a picture of labeled cells. This was acquired by Dave Basigi on an Amnis image stream. You can see here a dark field image, bright field image, so you can see the cell. And then 4 different fluorescences: a green fluorescence, an orange fluorescence, a red fluorescence, and a far red fluorescence. You can see the green, for example, spills over, and you can see it in the yellow and the red. The orange is bit in the green and the red, so on and so forth. So this is what the cells are looking like. This is what our detectors are measuring when we analyze something on an image stream or on a more traditional fluorescent flow cytometer that has either an APD or a photo multiplier tube. When we compensate, what we actually are then analyzing looks like this. And here now we're looking at a FITSI label because we've specifically focused on that fluorochrome. Our Sci3, Alexa Fluor 610 PE, and DRAC5. Nice and clean, no spectral crosstalk in any direction. So we're able to now interpret the data of one fluorochrome in the presence of the other fluorochromes. And that's ultimately what compensation is about. So why do we compensate? first off is the physics of fluorescence. So to remind you of your physics classes, a fluorescent molecule is one that when it absorbs a photon of light can release the energy by emitting another photon of light. So here we have a Jablonski diagram showing what that looks like. We have our electrons at our ground state, our fluorescent molecules just hanging out at ground state. A photon of light excites it. This molecule absorbs that light, promoting an electron to a higher energy state up here. After some non-radiative transitions, that electron is in this higher energy state, and since the molecule doesn't want to stay in that excited state, it needs to release that energy. Molecules can release that energy by vibrational, torsional, rotational energy. They can do phosphorescence, luminescence, or in our case, what we're looking at is fluorescence. So the wavelength emitted photon is of lower energy and therefore a higher wavelength of our excited photon. So this is the physics of fluorescence, and flow cytometry plays a lot with the physics, and compensation is related to the physics. Here's what that looks like. Here's our excitation curve. This is the curve for Alexa Fluor 488. Any wavelength of light on this curve can excite the Alexa Fluor molecule. Some are more efficient, like up here, about 490 nanometers is much more efficient than exciting this molecule than if we bring it down here to about 450 nanometers. That difference will impact the power of the energy of our emitted photon. The emission range, this is a probability curve of emission for this molecule. So if I excite this molecule with 488 light, 490 light, 450 light, I'm going to get the same emission curve. The height of that curve, the intensity will change with the power of the excitation wavelength and the laser power. You'll see this wavelength emission can go from this maximum point, this is about 520 nanometers, all the way out here to past 600 nanometers. So because of this broad tail, we need to think about how to address that. And that is where compensation comes in. And another reason we have to compensate is that we rely on gating tools, typically 1- and 2-dimensional gating tools. We can't, if we're looking at it as we're shown here, FTSE versus PE, we can't tell what's happening in any other fluorochrome on this plot because we're looking at the 2-dimensional plot. So if one of those fluorochromes is impacting the measurement out here, we could not tell that without compensation. And we want to make sure the non-displayed signals do not negatively impact our signal measurement. How do we measure that signal? Well, we measure that signal using most commonly a photomultiplier tube. And that's what's shown here. Inside a photomultiplier tube, light strikes a photocathode. If that photon is above the work energy of the photocathode, it will discharge an electron. And those electrons are aimed at these fins, shown in red, and these fins are known as dynodes. These have an increasing electrical charge across the dynodes, and as the as the electron hits the dynode, due to the principles of secondary emission, we get multiple electrons being ejected from that dynode. And you can see we go through an amplification process. So in this case, I'm showing one photon of light comes in, and when we get over here to the photoanode, we now have 512 electrons. So we've amplified this up by 512-fold. The photoanode takes these electrons and converts them into a photocurrent, and that's what we're actually measuring. So that photocurrent comes out, and an important thing to remember is that there's a direct and linear relationship between the photons hitting the cathode and the photocurrent coming out. And that's how come we can do flow cytometry and how we can make these measurements. Now, there are PMTs that can amplify 10,000-fold or more. There are some PMTs that can detect down to a single photon of light. But, of course, those are very expensive and require additional characteristics, such as very good cooling and keeping things extremely dark so that they don't have stray radiation doesn't affect them. So that's what happens inside the PMT. The APD does something similar and has a similar response, which is that there's a direct and proportional relationship between the photons hitting the APD and the photocurrent coming out. If I were to build a theoretical two-detector flow cytometer. Here I have my cell I'm showing. We're going to say, well, this is labeled with a fluorescein antibody. Our laser's coming in this way and exciting this cell, exciting the fluorochrome on the cell. The FITC fluorochrome emits light, and you saw a curve for Alexa 488. The curve for FITC is similar, and that's what these rays represent. Now I have two detectors, one here and one here. And because photomultiplier tubes will amplify any signal any photon that hits them, as long as it's above the work energy, we control the specific wavelengths of light that go to that PMT by using these filters here. In this case, a bandpass filter that looks at a range between 515 and 530 nanometers. Here's what the signal pulse looks like. Over on detector 2, we have a different bandpass filter of 58542, and we get another signal pulse, and this represents part of that tail that's being measured in this secondary detector. So this secondary pulse has to be removed, corrected for, so that we can measure this signal pulse in the presence of say we had a PE label as well, which would have its own pulse. Then again, that's what compensation is. To look at that and model that, here we see that curve. Here's our 530-30 filter. Here's our 585-42 filter. If we look at the percentage of the curve in each of these detectors, you can see about 46% of the signal is in this detector, and that's our primary measurement. But about 12% of the curve is in this detector, and that's what we're going to correct for when we go and compensate. And you can model these with any of the spectral viewers that are out there. You can put in your own filter configuration, and you can get this type of information to see how much area under the curve is in that filter. And one reason that might be useful is if you're using either a non-standard fluorochrome or you're trying to improve the signal on your fluorochrome or a signal on your detection, you may want to tweak these filters, and you can play with some of these filters to see which might be better and can improve the signal. With the newer generation instruments where you can easily replace the filters, it's a good exercise to do to see if that helps improve your signal. Now, moving on to compensation. There are three schools of thought that have been expressed about compensation. The first one is the idea called non-compensation, or that no compensation is needed. This is specific to the Accuray C6. It came out when the Accuray first came out due to some of the specific details about how that instrument works. It's really best for only single dyes, and if there's no significant mixing. So we're not really going to talk about that, but in case you hear that term, you know where it comes from. More commonly out there in the field is a concept of manual compensation, and this is what a lot of people who've grown up on some of the earlier generation instruments are familiar with. This is where we will manually adjust the compensation. We'll put a control on, and we'll manually adjust some slider bar or some number to affect our compensation. We'll talk about that, but there are some fundamental issues with manual compensation, and that's why the concept of automated compensation or computer-aided compensation came around. And some of the first papers published by this were back in early of 1993, but it wasn't until the mid-2000s that we actually started having automated algorithms to do this. And if you're going to do automated compensation, which is the best practice to compensate, you want to make sure you follow a couple of rules, and that's where these rules of compensation come from. So here's manual compensation. We're going to talk about this idea as my friend and colleague talks about, or cowboy compensation. So we're going to correct spectral spillover based upon best guessing, which, if we're scientists, it's probably not a good idea. There is a way to do this using matching the means or the medians, and I'll show you that briefly as well. As I said, this is historical, especially on the older analog instruments. If you're using something like a Excalibur or that, it often relied on putting a quadrant gate on your plot. We use on these earlier generation instruments, we couldn't see the full spread of the data, and because of that, we would oftentimes overestimate the amount of compensation we needed, and we're very error prone. So this is what cowboy compensation looks like. Here on the top, I have an uncompensated signal. I have a green signal on the x-axis and an orange signal on the y-axis. To manually compensate, I just start, sliding a bar. And as you can see, as I increase compensation going from left to right, this population here moves towards the axis and then keeps going, as you can see over here. This is clearly overcompensated. Not quite sure about here. These two are undercompensated. So how do you figure that out with this kind of cowboy manual compensation? This is all being done by eye. Not a good thing to do because we're going to overestimate our compensation values. So we can actually do this method using the statistics of the data. So here I'm showing, again, that same plot. Here I have a gator on a positive signal and a negative signal. My goal is to take the medians of these two populations. This is our positive population and this is our negative. And we're going to correct them into the secondary channel, down here, orange channel. And as we increase our compensation, you can see we start to move over until we get to these two arrows being close to each other or being off scale. Now here's the data so you can just see. You'll notice a couple of things about this data. You'll notice down here, this is the uncompensated signal. So this is the uncompensated signal of the FTSE, the green positives in the orange channel, the negative. And as we increase the compensation value, these both values start to decrease. Ideally, these two are going to match. You can see this here is overcompensated because they're not matching. This is way overcompensated, and this is undercompensated. So somewhere between 20 and 25% compensation is the appropriate value. We can figure that out mathematically by plotting a curve, as I'm showing here, where we plot the fluorescence intensity of our signal in the secondary detector over a range of compensation values. We compare that to the values of our negative population. We graph these two. You can look for the intercept or take the linear regression and solve for x, and that will give you the actual value. In this case, this solves for 24.445% compensation. Now, this is the median values on the earlier generation instruments. You couldn't calculate medians. So if you're using SalQuest, you couldn't calculate medians until the later generations of SalQuest. And then you had to stop and let it go through and calculate the median on the data as opposed to being refreshed on a regular basis. So you can imagine if you were going to do this for one population, you're going to collect at least four points, and you're going to have to make 8 measurements, 4 points per 8 measurements for one channel. You're going to have to do that for every pairwise combination. So you can see this can get tedious. What we learn from manual compensation, however, are the following. First off, it shows compensation affects all cells, even the negative ones. The compensation values will affect all cells because we're making a full measurement on each cell, and we're going to do a cell-by-cell compensation based upon those values. That cowboy compensation is the worst. It's error-prone and will lead to overcompensation. Manual compensation is difficult with 3 dyes and is really not feasible with more than 3 dyes for a variety of reasons. One of which is, as you compensate manually, you adjust one compensation pair, you put a compensation value in. You go to the second pair, now you're already dealing with a compensated signal, so you're going to compensate a compensated signal in a different channel and continue so on and so forth, and that's going to increase the error. And that's kind of highlighted here in this idea that statistical pairwise manual compensation leads to error in all the other channels. The bottom line here is avoid manual compensation. I know that there are people who will show you this when you're sitting in front of an instrument. The best reason to show you this is so you can see what compensation is doing to your data, but do not use it to actually compensate your data. We're going to talk about automated compensation, the best way to do this. And before I continue, there is a quick question. MFI needs to be defined. I use MFI as median fluorescence intensity, but if you read it in a paper, make sure they've defined it as either median or mean. There's no standard for that. So if I say MFI in this webinar, I'm talking about the median fluorescence intensity. And we'll have a webinar on data analysis next week, I believe. And we'll talk more about the concept of median versus mean and why we use one versus the other. So let's talk about the concept of automated compensation. So I'm going to take a step back for a second. Here we have tubes with cells labeled with a fluorescein molecule, a PE molecule, and a Cy5 PE molecule. This is what we want to know. How much green fluorescence, how much FITC fluorescence is on my cell of interest, how much PE is on my cell of interest, and how much Cy5 PE is on my cell of interest. How do I get that information? I put it on a flow cytometer, and I get an observed signal for the FITC, an observed signal for the PE, and an observed signal for the Cy5 PE. What are the relationships between these signals and these signals? Well, let's look under the hood, and here it is. The observed fluorescein signal is the sum of all the signals that are going to this detector. That means the FITC signal here plus the PE signal, and in that case times a constant M2.21, which is the amount of fluorescence from the second fluorochrome into the first detector, plus the amount of fluorescence from the third fluorochrome in the first detector. So this is what is the sum in the observed signal. How do we relate these to each other? Well, fortunately, we can do that mathematically, and we can do that through matrix algebra. Automated compensation ultimately calculates this matrix for you, and what we will actually have is, you can see we have our dye, FITC actual, PE actual, Cy5 PE actual, and we're going to multiply it by this matrix, and that would be all the signals from the first detector into the FITC channel, the second detector into the FITC channel, so on and so forth, and that gives us our observed signal for each of these. So you can see this can be actually the actual signal times this matrix equals the observed signal. And since we have the observed signal, we can just flip this around, and it turns out that the actual signal is our observed signal times the inverse of this matrix. All of this is happening automatically for you in the background. We don't have to do the matrix algebra and don't have to do the pairwise matrix comparisons. We just have to make sure we feed the system the best controls possible. And we're going to now start talking about the best practices in compensation. But before I do that, I just want to remind everybody that if you get on our mastery class waitlist during this webinar, you'll get access to that compensation and control webinar bundle that Isaiah talked about. My colleague Kathy is going to post that link as a reminder. So there it is in green at the top. Thanks, Kathy. If you join on that wait list, you'll get more information about what's coming up in our program, and you'll get that 2-webinar package on compensation and controls. So let's move forward. You may have heard of the 3 rules of compensation. These have gone around the internet a lot. And they were originally posted on a blog by in the FlowJo website, the Daily Dongle, as I call it, but this has been propagated around for a while. So let's review these 3 rules, because if you're going to get good compensation, you need to follow these 3 rules. And in my experience, anytime people come to me and they say that they have a problem with compensation that they want to fix manually, it's because one of these rules has been violated. And so we need to track down what rule was violated and make sure that we correct that violation. Rule 1, controls need to be at least as bright as any sample you will apply compensation to. What do I mean by that? Here's an example. Over on the right, I have my compensation control. I've put a blue line across the compensation control to show you the median fluorescence intensity of that compensation control. And look, on our fully stained sample, here's our population. I've drawn a red line showing you the median intensity, the diagonal here. These cells are clearly undercompensated, and that's because they're brighter than the compensation control. So when you see a situation like this, you have to ask yourself, what happened with my compensation control, or what happened with my cells? This happens sometimes when you have stimulated cells. During your panel design process, and we'll talk about panel design in a different webinar, one thing you would want to do is test out your antibodies and your compensation to make sure that you don't have this situation. And that's an important step to remember as part of the process. Further on that, brighter is better. Here we're looking at fluorescein versus PE. Here's our negative peak. Say we have a dim population and we have a bright population. We're ultimately calculating the slope of this line, and how good this line is and the slope of this line is going to be in part dictated by the spread of the data and how accurate we can make a measurement as to the central tendency. The dimmer the particles, the wider the spread of the data, because less of the photons are converted into photocurrent, and more importantly, with the fewer photons that are converted to photocurrent, the higher the CV, higher the spread of the data. That's based upon Poisson statistics, that the more photons you have, the better the CV. The fewer photons you have, the wider the CV. So at a very bright signal, we have a much better measure of the CV, so we get a much tighter signal, so we get a more accurate compensation value. You can see even, this difference is just a slight difference, 24.83 versus 25.14. But this would overcompensate these cells because we're made the wrong compensation value because we had a less accurate measurement. And that's why we always want to use brighter, and we say brighter is better. The second rule of compensation is that the background fluorescence should be the same for the positive and negative control populations for any given dye. Now, we can use different carriers to get the fluorescence to our laser intercept. Here I'm showing the background fluorescence in two detectors, our FITC and our PE detector, of beads shown in red and cells shown in blue. You notice right away that the tightness of these populations, the beads are much tighter than the cells, and so they're going to have different fluorescence intensities. And so, like I said, the better the CV, the tighter the population, the more accurate we can make a measure of the central tendency, the more accurate we can make our compensation, which is why we use brighter. And on this side, let's take a look at the consequences. Now, I'm plotting these two data points the same way that I showed you earlier in the manual compensation to illustrate this point. And this population here, we use that bead as our negative control. Our cells were our compensation control was run on beads, so they were positive. And now I'm comparing the positive signal to a background signal that is based upon the beads. And you can see here, we get a nice slope, and we get our intercept of 24.82. Now, when I calculate it using the beads as a positive and the cells as a negative, and you'll recall that we saw a very broad spread in that data, so we have a less accurate measurement of the central tendency. In fact, it was slightly higher than the beads when we looked at it. We see a slightly different intercept, in this case 24.68. So there's a definite difference between the beads and the cells, and we are violating the second rule if we use something called the universal negative, or we and track all our positives to one negative. And I'll show you some of that in a little bit more detail. Third rule is that your compensation colors must match your experimental colors. And this means your identical fluorochrome, identical instrument sensitivity. Here's an example just showing you, this is data from Accuray, that all greens aren't created equal. We have GFP, FITC, and CFSE acquired on this instrument. And you can see as we start to apply compensation, when we apply compensation to properly compensate our GFP signal, our FITC and our CFSE signal are not compensated. They're undercompensated. When we compensate our FITC signal, shown here, our GFP is overcompensated and our CFSE is still undercompensated. By the time we properly compensate with the CFSE, these other two fluorochromes are overcompensated. So you cannot use, in this case, FITC to compensate GFP. That even goes down into tandem dyes. So in the case of something like PE Psi 5 or Texas Red Texas Red PE or Alexa 700 APC or some of the Brilliant Violet dyes, the Brilliant Violet 650, Brilliant Violet 780 something, and so on and so forth. The brighter, the farther red Brilliant Violet dyes are all tandem dyes. So you want to make sure that the tandem dye is the identical dye that you're using, because each tandem dye is manufactured, is man-made. There can be different labeling efficiencies and different ultimate spectral spillover between those different dyes. So you want to make sure you use the same dye. I'm hoping to end about a little after 11, but I'll have some time for questions. And yes, you will. Those of you signed up, you'll get a link to watch this webinar again. So let's talk about some further considerations in compensation. This is that idea of the universal negative. Certain software packages take you down the road to collect a single unstained tube for your negative populations. If you're running a DIVA-based instrument, that's one of the first things you have to make a decision on when you compensate. If you're compensating in some of the software packages, they will ask you, do you have a universal negative? Or they'll drive you to this idea of a universal negative. So take the scenario where I'm staying in a multicolored panel. I have my antibody stained on an antibody capture bead, but I'm also using a viability dye like DAPI, or I'm using GFP, or I'm doing a proliferation assay like CFSE. So I have to use cells for those. So if I collect a single tube, for example, here is my single tube, and this is my universal negative, and here are my beads, you can see the fluorescent intensities. We're going to be correcting the fluorescence intensity of this channel into the PE channel. If we use our universal negative, we have a compensation value of about 2.6%. If we use the proper bead control, our true compensation value is about 6.4%, and we see some significant differences in the populations here. This goes from 57 to 62, and this goes from 30 to 24. So it's best practices for you to have a positive and a negative population in each compensation sample. So you can set a positive gate and a negative gate. And that way you are ensuring that you're not violating the second rule of compensation. One of the great myths of compensation that I've heard is, oh, you can't have compensation over some number. Some people say 40%, some people say 60%, some people say 100%. Compensation is a mathematical measure of the spectral spillover of all the fluorochromes in the panel into your specific channel of interest. So if you go and model something on a spectral viewer, throw up something like PE, and then look at potential impact of FITC, Psi 5 PE, Psi 7 PE, Psi 5.5 PE, Texas Red PE, you'll see that all of them have the potential to spill over to be measured in that PE detector. Here we're showing a compensation matrix, and you can see in red some of these detectors are over, some of these values in this compensation matrix are over 100%. People have this tendency to want to change the voltage to make a better impact on the resolution, and that doesn't actually work. That just impacts, that doesn't affect the compensation and does not make the resolution better. So as part of the best practices in optimizing the assay, you want to optimize the voltages for each detector before you actually put the panel into play and work through the issues. The increase in compensation here, you may want to consider redesigning the panel because you may be losing sensitivity. But if the signal doesn't impact in that, don't worry about it. I mean, it's a mathematical model, and don't be scared of a compensation value over 100%. I've published papers on this. Others have published papers with compensation values over 100% without a problem, and you can measure the signal very easily. This is just showing you uncompensated versus compensated, how things look between when we have, in this case, over 100% with some of these fluorochromes. And you can see clean compensation versus uncompensated in blue, compensated in black. You get nice compensation even though you have 100% or more compensation value. Another common misconception in compensation is that compensation leads to error, and it introduces error into our measurement. There is error in our measurement. There's error in every scientific measurement we make. What happens in compensation is that we reveal that error of measurement because we shift our visualization of our data from the high end of the log scale to the low end of the log scale. So here, for example, I'm showing you uncompensated data. I'm taking a dread line. I'm showing you at this specific channel, and I asked software to give me the 5th percentile and the 95th percentile of that specific channel. And the 5th percentile is 1859, and the 95th is 2730. So this difference here of 872, you can see where that difference is. When we properly compensate, we need to maintain that spread. So here's what the proper compensation looks like. Here, we're about 436 fluorescent units. So if we're going to keep up that whole 872, we're going to be a little bit below the axis. Why can't we see that? What's going on? Well, let me magnify, and this is using FCS Express. It's got a great magnify tool. You'll notice here with this red population, we've got a lot of cells accumulating on the axis. For that reason, researchers have developed several different ways to visualize the data around that 0 point. And I'm showing you here one of the common ones, the biexponential method. And you can see here, by applying the biexponential visualization, the transformation, we are able to visualize now the full spread of the data. And I told you there's our 872 units of separation or spread that up here, when we were uncompensated, was much smaller. But that's the same amount of spread. We haven't added more error to the data. We've just made it more obvious because we moved to a different part of the signal. Now there's a different part of the log scale. Now there's a variety of different ways to do transformations. The biexponential is one of my favorites. There's several variations, the Lin log method, the hyperlog, which is another very good one. The arcsine method, which I'm showing here, not a huge fan of on fluorescent data. It works very good on mass cytometry data. If you're using the CyTOF. But best thing for you and best practices is to identify the transformation that you're going to use and be consistent in its application. And that means that throughout your whole analysis, you keep the same settings for the negative part of the axis so that you are looking at the same thing. So we don't have to worry about compensation over 100% because we can address it. We can visualize it. We don't have to worry about this idea that compensation introduces error. It reveals the error. Another common misconception is that I can reuse a compensation matrix. I can run a compensation matrix on day 1, and 4 days later I can use the same compensation matrix. Well, that's not best practices. It's not a good idea because there's a variety of changes that can happen over time. Compensation is going to be affected by the laser power. If the laser power changes, what happens there? The PMTs, you've got to make sure you've got the same identical voltage, because if we use different voltages between days, we violate the third rule of compensation because we haven't acquired the data under the same identical sensitivities. People get the machine dirty. There may be other problems. So very, excuse me, very important to create a matrix every day. Here is an example of reusing a matrix, or the differences between a matrix on 2 different days. So these are the same cell samples, a frozen sample, thawed, stained with these fluorochromes, PE, Cy7 PE, FITC, Cy7 APC and APC, and DAPI. We ran the experiment on 1 day. The machine here was kept under very tight control, very good, consistent data on the control data, which I'm not showing here. We ran the same cells, same staining panel, same technician. A week later, these are the same antibodies, just a week older. And I've plotted down here the difference between these 2 dates. And those in black show that the date 1 was higher than date 2. Those in red show that day 2 is higher than day 1. And you can notice here, for example, blue F, nothing really major. But down here in this blue H, we have 27, 28, and 12% difference compared to the first one, the first matrix. So you can't exchange matrices across days and times. So best practices is to create a matrix every day. Another question is, I can only use cells for compensation. It's another myth. I can only use my cells for compensation. Well, what the important point is, it doesn't matter what the carrier is. It doesn't matter how I get the fluorescence to the fluorochrome to my laser intercept. I just need to get it there. I can use cells as a carrier. I can use antibody capture beads, APCs, or ACPs, to get that there. So the advantage of cells is you actually know the autofluorescent background, so that you can make sure that your positive signal is above that autofluorescent background, and you can get a good, you're able to have a good signal. Disadvantages shown here are the CVs may be less sharp. Where do you put the gates for positive versus negative here? Excuse me. And that may be minimal separation here. You're going to use your precious sample for compensation controls. I'm using hematopoietic stem cells that are 0.1% of the population. How many of those am I going to need to set up a compensation matrix if the signal I'm interested in is on those cells? Few target cells, say you're looking at cytokines. Maybe you only have 10 cells that are producing the cytokine of interest in your assay. How many of those are you going to need to run to actually have sufficient numbers to ensure that you're getting the best signal possible and that you're capturing the most data possible to have a good, accurate measurement, and you're not having a poor CV. Now, antibody capture beads, which is what I like, which I use for almost everything. First off, they don't waste cells as a control. I get 1 ml of blood to stain for an assay that we do. 1 ml from a patient, that's all we can get because these are premature babies. So I'm not going to want to waste the cells from that tube to set up compensation when I can easily use beads for that. Beads are easy to use. You can buy your favorite bead from BD, eBioscience, BioLegend, Bang, Spherotech. Check who you like. Talk to colleagues. Ask for samples. They capture the maximal amount of antibody in the sample. So we don't violate Rule 3. We get the best signal possible. We don't. So we're not violating Rule 1. We're getting the brightest signal possible, and we're capturing the identical fluorochrome. Again, not so we don't violate Rule 3. Do check what your beads are going to target. Some target only the light chain. Some only target the heavy chain. Some only specific species. But you get very good separation, very tight CVs. It's very easy to set a positive and negative here. They can be somewhat problematic for two-step reactions. And when I say that, it's not because they don't work. They work great. It's because if you put a drop of beads in a tube and you spin the tube down, you don't necessarily see the pellet as opposed to if you put 1,000,000 cells and stain 1,000,000 cells and you see a nice pellet. So you may think you've lost your beads. If you're going to do a two-step reaction with beads, make sure you mark the tube orientation so you know where the pellet should be. And even though you may not see it, you don't decant it or aspirate it. So where do you compensate? This is another common question I get. So if we think about it, there's two places we can compensate. We can compensate during the acquisition when we're acquiring the data on the instrument, or we can compensate after the fact, post-acquisition compensation. So the reasons you might want to compensate during acquisition is so you can monitor the experiment during the run. You can identify potential issues with your sample and resolve them. Of course, that means you're going to spend more time at the instrument, and in some cases, time is money. If we're charging you $50 an hour and you spend 15 minutes compensating, that's 15 more minutes you're going to have to pay for that. The other reason I don't like to compensate on the instrument is because you're going to have to redo the analysis. You compensate on your acquisition software, you're going to go back to your lab, and you're going to have to recompensate you're going to have to redo the analysis anyway in your acquisitions, your analysis software. Of course, you do have to do this when you're sorting. I like to do my post-acquisition compensation because I can get more accurate measurements. I'm able to be much more precise. I don't like to use histograms when I compensate. Compensation software tends to drive you to use histograms. I like to use a bivariate plot, a two-dimensional dot plot, so that I get a better signal and I can see I have a better visualization of my positives from my negatives. I save time on the instruments. Like I said, I get better identity of my populations. And of course, in all the cases here, you want to avoid the universal negative. So before I take some questions, I see there's some that have been popped up. I want to give you some summary, and I'm going to leave you with some best practice. Oh, sorry. That's what happens when you, I hope I'm not making anyone sick. I have the Apple mouse with the trackpad on it, and sometimes I get a little bit fast with that. I apologize. Here we are, summary and best practices. Compensation is due to the physics of fluorescence, so we have to address that so that we can make a best measurement of a single fluorochrome in the presence of other fluorescent spillover. Automated compensation is the best practice. You want to avoid the error-prone manual compensation because that will lead to, more often than not, overcompensation and incorrect interpretation of the data. People, again, in my experience, if people have compensation problems, it's because they've not followed the 3 rules of compensation. That is, the control needs to be at least as bright as a sample. It also has to be on scale. So you need to make sure that your compensation control is on scale, because if it's off scale, obviously you can't make a measurement, an accurate compensation measurement. The backgrounds of the carriers must be matched. So you want to avoid the universal negative. And if you're using a bead for a specific color, for a positive sample, you want to make sure you have the same bead unstained as a negative sample. The third rule, the compensation colors must match the experimental colors. As I showed you with the GFP, FITSI, CFSE, even though they're all green, they have slightly different spectra. Therefore, you can't use one for the other. And this is even more important when you start to use tandem dyes. And make sure you know what your tandem dyes are. Not all of the tandem dyes are named as in the standard convention of 2 fluorochromes. For example, Sci5PE is a tandem dye. Brilliant Violet 650 is also a tandem dye, but it's not named that way. So you want to make sure you know which is right. As a bonus, you want to collect a sufficient number of events. Try to emphasize the idea that compensation is making a statistical measurement, and the more accurate that measurement is, the better a compensation is. That's why we want to have bright signal, because we want to avoid a large error due to photon counting statistics. And we want to have sufficient events so that outliers are not negatively influencing our data. To that, I mean at least 5,000 I'm sorry, at least 10,000 bead-based events. Don't rely on the default 5,000 that, if you're using a Diva instrument, that defaults to. And a minimum of 10,000 bead-based events and a minimum of 30,000 cell-based events. Last but not least, the carrier doesn't matter. Whether you use beads or whether you use cells, it doesn't matter as long as you have the carrier match, the positive negative carrier match, so you don't violate the second rule of compensation. Now, I'm going to remind you, before the webinar is over, there's that green box where you can sign up for the mastery class, where you can get access to free to those two webinars on compensation and control, so you can review those at your leisure. Our mastery class will be opening up soon. This is this online training program that Isaiah talked about, where you can take this at your leisure. We have, I think, close to 100 hours of online training videos now, broken down into a core set of modules that include quizzes, workbooks, PDF downloads for those. We have an ongoing webinar series. We have webinars approximately every 2 weeks, and we bring in experts in the field. I can tell you, this winter, it's winter in Rochester, so this winter, end of February, Ryan Brinkman from Vancouver is going to be talking about automated compensation methods. We have a colleague, Regina Nuzio from Gaudet University, who's going to be talking about statistical methods to give us a primer on statistics beyond just let's do a t-test or let's do ANOVA. We have additional talks coming in on other advanced analytical techniques, high-dimensional data analysis, best practices in single-cell sorting to go to genomics, and so on and so forth. So we're continuing to expand what we offer and continue to get the best experts in the field to speak. And you can see, again, this is what we have here, those core modules, the workbooks, our training videos. We also have a private Facebook group. If you are using Facebook, I honestly, I have a personal Facebook group so I can see my granddaughter grow up. But the private Facebook group, they have a great, Facebook has done a great chat system. So if you're a member of the mastery class, you can get into this private group, and we post questions. We talk about issues in cytometry. We present best practices. We talk about papers. If you've heard of the certification of cytometry, earlier last year, we spent 3 weeks going through the different topics that are related to that certification of cytometry, reviewing the ideas and concepts behind that. You have a problem, it gets posted, we talk about it. We had an example just 2 weeks ago. One of our masterclass members had submitted a paper, and a reviewer came back and specifically said the reviewer was upset that there weren't any isotype controls used to set gates for the data. So the group collectively helped him build refine his argument to show this reviewer why isotype controls were not useful, and including with references and details. And that's something we'll talk about in a control lecture coming up. So there's a lot of useful information here, I really think, and we really continue to keep it as active as you want within the page. You can be as active in the private group as you want or not. If you're on the Purdue list, this is a little bit more directed than the Purdue list. So before I start answering questions, again, last course to remind you to get this advanced compensation bundle if you're interested. So click that green signal up there. So I'm going to start going through a couple of questions to see. If I miss your question, I do apologize because we have a lot going on. And you will also get a link to review this video in case you have any other thoughts on you want to review it. Brent asked, how do you permit compensation if over 100% infects Diva when you get a calculated compensation throws up an error? This is why I don't actually compensate in Diva, Brent, except when I'm sorting. We actually saw a problem in this where Diva would throw up a problem saying that compensation was over 500%. But when you pulled the data out and put it into third-party software package like FCS or FlowJo, and you were properly identifying the positive and negatives, the compensation values were quite reasonable in the 30 to 40% range. There was something weird going on with that in Diva 6. I haven't seen it yet in Diva 8, but I would rather compensate offline. Likewise, Diva doesn't make it easy for you to not use a universal negative. You have to remember to uncheck the box and then draw the quote P3 gate on your compensation control, so the software then knows to use the P3 gate as the negative, and you need to draw a P3 gate for each tube, which is why you need to have a positive and negative in it. So that's why I don't like to do that. Diva, depending on how far it is above 100%, will let you still move forward with the automatically applying the compensation. Best thing to do, if you do get that problem, look at your controls. If you're really concerned, pull the controls out, throw it into your third-party software, run the matrix there and see what's happening. But just acquire your data without compensation and analyze it retrospect or on post-acquisition. Vanessa asks, how do you compensate autofluorescent cells? If you're asking, how do I take an autofluorescent cell and use the autofluorescence as compensation, I would need to have a non-autofluorescent cell of similar characteristics to do that. Traditional fluorescent flow does not deal with autofluorescence compensation as well as some of the newer technologies coming out, especially the spectral analyzers from Sony and Cytek. We actually had a talk about the Cytek instrument that really went into detail why on spectral analyzers, autofluorescent signal can be more easily addressed than in a traditional fluorescent flow cytometer. Sean asked, does compensation matrix still apply if you use a cytometer setup and tracking daily, and the matrix automatically updates based upon the values recorded? You must recompensate every day. CS&T change, if you set up application-specific settings, will readjust the voltages based upon the changes in the software, in the measurements that CS&T makes. So it will move those values up and down. The third rule of compensation specifically states that you need to be capturing under identical sensitivities. Changing the voltages a few percentage will affect those settings. I would not want to try to publish a paper where I ran a compensation matrix once and applied it over multiple days. That being said, if you do the work and you prove to yourself and you have the data to support this, that you don't have to change, you don't have to do that because your system is running in a certain, consistently in a certain manner, then you can do that. But you have proven to yourself that it's working. And so then when a reviewer like myself says, this isn't the best practice, you need to compensate every day, you have the data that says we've shown that on this instrument we can consistently get the data and compensate accurately. But in general, that doesn't happen. And I will tell you, we run I have a fleet of 5 LSR2s, 2 ARIAs, and those are kept under very tight control. And even so, we see drift in the systems due to any number of things. Even the temperature in the room can affect your system, especially affecting the negative, the background. PMTs, if they get too hot, can start to have random secondary emissions, and you want to make sure that that isn't affecting it, your signal. Because what's going to happen if you have these background current, you increase the background fluorescence. Jamila, if I said your name right, is using a Cytoflex and this whole idea that you can create a library to create a new matrix. Not a happy fan of that. There's some definite issues with that a colleague has shared with me, and we're trying to finalize some information on that. But I do not. The argument is that the APDs are absolutely linear over the dynamic range, and so therefore, mathematically speaking, if I set up a compensation matrix at value X, because I know the absolute linearity of the system, I can automatically calculate the new value. But that's not true on the system, and that's not true that they're not absolutely linear over the whole range. So there's definitely some issues with that, even though they talk the Beckman-Coulters talked about that. Christos asks, it can be argued that if your cells of interest do not express bright levels of marker, then there's no point compensating with a bright signal, since you will really only deal with a dim signal in the real data. Christos, best practices is to use as bright a signal. It's got to be at least brighter than your experiment that's going to be applied to your experiment. If your signal is at 10 to the third for your experimental, as long as your positive control is above 10 to the third, you're going to compensate accurately. Maybe it's not at 10 to the, at the far end of the spectrum or far end of the scale, but it's got to be at least as brighter. The fact that you use the brightest signal possible means you're getting the best, the best measure, the tightest CV, so you're getting the best measure and calculation on that line to compensate accurately. Bianca asks, when compensating in FlowJo or post-acquisition, and there are shoulders on the histogram, do you gate the entire area or just the tightest, brightest peak? As I mentioned, I don't use histograms. I actually set up my compensation matrix using dot plots, bivariate plots. So I'll plot the primary signal, fluorescein versus side scatter or versus something else, so I can see the full range of the population. And I use a rectangular gate to get the whole population. I don't like to use shoulders. I don't like to use histograms for that purpose. I want to know what's going on. And by using a bivariate plot, I get the much more accurate measurement, better visualization to set my gates better. Christos asks, are all brilliant violet tandems or only 650 and 785? I just mentioned those as examples. The base brilliant violet dyes, so the brilliant UV 395 or whatever that is, 421 and I think it's 510, are all the base brilliant violet dyes. Those are not tandems. All the other brilliant dyes above those wavelengths are tandem dyes. If you go to the spectral viewers like the BD spectral viewer or the BioLegend spectral viewer, and you look at the spectra of the far red tandem dyes, you will see the two excitation peaks. That is indicative of a tandem dye. Samir asks, can you analyze data on a non-compensated sample using a single stain control and FMO controls if you do not have enough cells for compensation? Samir, move to beads so you don't have to worry about that problem. Now, I would not recommend what you're suggesting here, analyzing the data on an uncompensated sample using single stain samples and FMO controls, because you're not going to have a good accurate measurement, and you're not going to have a good measurement of the spread of the data that may be potentially impacted because of the other fluorochromes in the channel. So you want to use, I recommend that you use beads for that. Marina asks, can you use other cells in your rare cells for dyes that don't work with your beads? That depends on the expression of the antigen that you've targeted tied to the bead on your cells. So, for example, if I'm looking at a fluorescein labeled CD34 for human hematopoietic stem cells in the human, and I use CD3 FITC on T cells to compensate, as long as I have a positive or negative T cell, I'm okay. But now flip forward to that where I used PE-Cy5 CD34. I cannot use PE-Cy5 CD3 because that violates the third rule of compensation. I really, again, I would move to the beads, and if your dye doesn't work with beads, you need to think about why it's not working with the beads. Now, if it's CFSE, fluorescent protein, a dye like a nuclear dye like 7AD, and that, then you need to use cells. And as long as the cells, you have a positive or negative control, and so that you don't violate the second rule, and that the signal is at least as bright as on your cell, or brighter than on your cells of interest, then you can do that. I'm looking at the time. It's 11:15, and so I'm going to answer one more question, and then I'm going to have to head off to the rest of my day and let you go back to the rest of your days. And again, I really appreciate you joining me today. We'll be having another free webinar next week. You'll see information about that. We'll be talking about data analysis. Anna Carmen asked, do I have to compensate when I use the same laser but two far dyes on the emission spectrum? If you have two dyes in your panel, you must compensate. Even if the compensation is very, very small, you should run your compensation matrix. For example, even if I have two dyes on two different lasers, FTSE off the 488 and APC off the 633 laser, I will still compensate. Even though FTSE is not excited by the 633 laser and APC is not excited by the 488 laser, I will run the compensation to make sure that I am accurate. And that way I have a control that gives me confidence in my data. So thank you, everybody. There's a lot going on here. Again, I thank you for your time, and I hope to see you next week. Have a great day, and we'll talk soon, I'm sure. And there's one more second. I'll give you just expertcytometry.com mastery class to be able to get this 2-pack bundle. Thank you much.